Today we're going to check out the first steps of diagonalization of a matrix. So we're going to find lambda, a matrix where all of the eigenvalues of A are displayed on the diagonal. So lambda 1 to lambda n over here. Let's go. When a matrix is diagonalizable, it can be expressed in the form A equals S lambda S inverse. First, recall the definition of an eigenvector and its corresponding eigenvalue. AV equals lambda V. If you're a little shaky here, check out my previous video where I explain this equation. Okay, so we can now come up with a new matrix, S, which is made up of all of the eigenvectors of A. So we just put them in here, V1, V2, up until Vn, and make up a new matrix, S. Moving on. Next, we can multiply A with S, which means that we apply A to each of the eigenvectors. So we have AS, meaning A times V1, A times V2, and so on. And now, since each of the eigenvectors satisfies the equation AV equals lambda V, we can also write it as A times V1 is the same as lambda 1 times V1, A times V2 is the same as lambda 2 times V2, and so on. So this is another way of writing it. Next. And now if we extract all of these eigenvalues and put them in this diagonal matrix, we get this matrix over here, which we were showing in the beginning. So lambda equals the matrix with eigenvalues on the diagonal. So the equation AS equals S lambda holds. Now let me show the same steps, but with Python SymPy. So first of all, we just load a sample matrix over here. This is the easy step, so just give it these values and say sp.matrix and display the matrix over here. So we have the sample matrix for 1, 6, 3, matrix A. Okay. Then the next step is to compute the eigenvalues and the eigenvectors. Let's run this code, and you see it's just a.eigenvalues or a.eigenvects. We display it over here. So eigenvalues returns the eigenvalue, including the algebraic multiplicity. So we have eigenvalue 1 over here and eigenvalue 6. Both have multiplicity of 1, meaning that we don't have any duplicated eigenvalues, meaning that we can diagonalize the matrix. So this is a good result. And eigenvectors returns the same, but it adds the eigenvector at the end. So we have the eigenvalue, algebraic multiplicity, and the eigenvector at the end. And here the same. Okay, moving along. So next up, we can construct the matrix S. And the columns, as mentioned before, are the eigenvectors. So we create this dictionary over here, and we write into it the vectors. So this is the second part here, and map it to the eigenvalue. So we have eigenvalue and eigenvector over here. Let me print this. Okay, so we now have here the eigenvalue and the eigenvector, eigenvalue, eigenvector. And then we can create a new matrix, like the matrix S, only with the eigenvectors. So we use this command over here and just add eigenvector dict 6, so the eigenvalue 6 and the eigenvalue 1 and their corresponding vectors over here. So we have matrix S now, the matrix with the eigenvectors. Okay? And then step 4, we construct the diagonal matrix lambda. So this is just to compare later and show proof that it's actually correct. So I'm just taking the eigenvalues that we extracted before. So these ones here, 1 and 6. And since we decided to go for this order to have 6 first, I'm putting in 6 first and then 1 second and print this one. See, diagonal matrix lambda with the eigenvalues. So we have 6 and 1 over here. And now the final step is to prove that this equation actually holds. So we verify the diagonalization here, and we prove that these here are the same. A times S and S times lambda. Let me see if this actually holds. And as you can see, they both produce the same matrix, so the equation is correct for our demo case here. Great, now we've proven this equation, and in the next video I will actually show you what to do with it. Stay tuned, thank you for watching this video, and don't forget to like and subscribe. See you next time.